some stupid shit. It's nothing important there. So then, so basically, okay. So, in for neurons, there's in the CNS basically there's the glial cells and then there's neural cells, right? Well, in any type of neurons, there's gonna be the neurons and gonna be the glial cells. Glial cells are basically the helper cells, and the neurons are the ones that kind of relay information, process information, receive information, as in neural information transmission, right? And commands the body's how to respond. So basically, in the Golgi stains, it kind of reveals the soma and also what we call a perikaryon. So soma and perikaryon, they're combined together and there's something called a neurite. So neurite is composed of the axons and dendrites, right? And sulfate staining has resulted in a black deposition within that the neurons itself, they're not a continuous system. They're kind of like discrete system in which they're connected by a synapse or synaptic cleft. So they're not they don't communicate by physical contact, but by discrete. They're discrete entities. Yeah. And so what they found is that in here you can see there's a lot of these vesicles that are docked near the synaptic end or synaptic terminal of the axon, and a lot of these dense core vesicles. The dense core vesicles inside of them are basically peptide crystals. So if you see in here, the difference between axons and dendrites is that axons are usually already thinner in the first place, and they tend to be longer than dendrites, and they don't minimum branching and they don't taper out. For dendrites, they make the neurites, and then the action potential is generated from the axon hillocks, and from the axon hillocks they travel down the axon proper, which is the middle part of the axon, and until they reach the axon terminal. And so the difference between the axons and the soma is that in soma there's the ER and the Golgi. There's no Golgi or ER in the axon itself, and specifically at the axon terminal, they don't have the microtubule. Within the vesicle, and the what else in there? Vesicle, mitochondria, and a lot of the membrane-bound proteins, right? Like channels or receptors, like the calcium channel. The microtubules basically transport all of the necessary components like the mitochondria or the vesicles or the neurotransmitter or any proteins necessary to be transported towards the axon terminal, right? Then there's the mitochondria in the axon terminal. It's discrete, it's not continuous, and yeah. And then the soma, I already know all of this. This is some stupid shit. This is so easy. This part is easy. Yeah, cytoskeleton, there's the neurofilaments. There's the microfilaments, like microtubules. So microfilaments is also called actin, and also we have neurofilaments. Axon hillock, axon proper, axon terminal. The ER does not extend into axon, protein composition unique, and no microtubules in terminal, blah, 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 blah. I already know all of this. Axoplasmic transport, I already know all that. The synapse, I already know that. The distance between synapse like 20 nanometer or something like that. Right, the classification of the dendrites, of neurites. So there's gonna be unipolar or bipolar or multipolar. Yeah, so basically, if you have more than one neurites, you call them multipolar, two or more. And unipolar is where you only have one neurite. And then there's stellate and pyramidal cells. Stellate cells are usually the one that look like stars, and pyramidal cells are the one that looks like pyramids. And classification based on the axonal length. Remember that Golgi type 1 is usually a very short, right? No, long, sorry. So Golgi type 1 is the one that has long axons. Golgi type 2 is the one that has a very short axon. And then there's also Gray type 1 and Gray type 2. Gray type 1 is the one that is asymmetrical, I believe. And yeah, stuff like that. glial cell, I already know this. So in the PNS is the myelination in the PNS is by Schwann cells, while the myelination in the CNS is by oligodendrocytes. And yeah, oligodendrocytes, they make the node around here for this saltatory conduction here. I already know all of this. I already know all of this shit. It's easy. That part's easy. Neurons and glia's part easy, and saltatory conduction. I just want to make sure the name is actually saltatory conduction. Right. Wait, let me search saltatory conduction. Is it right? Saltatory conduction? Saltatory. Yep, saltatory conduction. So, chapter 3 now. So basically, chapter 3, action potential. So as you can see here, this is somatosensory. We're not going to talk about that today. So anyway, these shit's easy. Oh, right. With regards to ion channels, so there's the ion channels. It's very selective for sodium ion channels and potassium ion channels. They're selective towards their own respective ions, right? So the thing that makes potassium ion channels more selective towards potassium and sodium cannot get into the potassium ion channels because the sodium ion is more concentrated in charge because of the smaller size, which means it's better hydrated because it attracts more of the water molecule. So there's a bigger sulfation cell, and this bigger sulfated sodium ion cannot pass through this potassium ion channel because of its size. And what makes the potassium ion cannot pass through the sodium ion is that because in the middle of the sodium ion channel, the sodium ion is actually stabilized by interaction, by polar interaction, ionic interaction with the glutamate. Was it glutamate? I don't know. Carboxylate residue of the amino acid on the protein structure, and it's stabilized alongside with the water. And so this stabilization part only fits the sodium ion and the water, and the potassium ion is just too big to be stabilized at that part. So the transient stabilization can only occur with the sodium ion and water, and potassium ion and water cannot fit into that transient stabilization part. And so that's why it's selective towards the sodium ion. And I remember that for the ion channel, can act as a resistor and also as a conductor because it resists the ion flow when it's closed, and it also conducts the ion flow when it's open, right? So it can act as a conductor or a resistor. And in terms of type of ion channels, there's the ohmic ion channel, ohmic channels, or rectifying channels. So ohmic channel is the one that follows the ohmic law, V equals to IR, so the voltage equals to current times resistance, right? While the rectifying channel means that it favors the current in a specific direction. So there's a low conductance and high conductance. So example of the rectifying channel would be the potassium channel, when it basically resets the the membrane potential at the end of the action potential, when it polarizes the cell, and it favors the current flow of the potassium ion outside of the cell. So that's why we call it a rectifying channel. And then types of ion channels, there's ligand gated ion channels, there's the neurotransmitter gated ion channels, there's the voltage gated ion channels, there's also the mechanical or pressure gated, stretch or pressure gated ion channel. Also the phosphorylation gated ion channels. So depending on phosphorylation or not, it will basically open. So phosphorylation, ligand binding, voltage gated, and also pressure or stretch gated. And then the channel proteins, basically the polar groups, the polar amino acids are hydrophobic amino acids. The hydrophilic amino acids are located on the inside cavity of the channel, and hydrophobic is outside. And the difference between channels and pumps is that pumps usually use ATP for the transfer of the ions or the molecules itself. So yeah, so the movement of ions, I already know this. Yeah. I already know all of this. So equilibrium potential, the Nernst potential is basically at the equilibrium potential, there's no net ion movement. So that means that there's no net movement of ion. No net movement of ion. Yeah. At equilibrium potential, there's no net movement of ion. Equilibrium is reached when so for example, the equilibrium potential or reverse potential of the potassium ion is like minus 80, minus 80 millivolt. And so at minus 80 millivolt of the membrane potential is like at minus 80 millivolt, that means that there's no net movement of this potassium ion. So that means like although there's a lot of the potassium ion inside of the cell, and the chemical gradient favors the efflux of the potassium ion, the electrical gradient, because it's too negative, it makes the potassium ion stay. So the chemical and the electrical gradients are equal and acting at the opposite direction, which makes no net movement of the ion itself, right? So that's what equilibrium potential means. So when it goes below that minus 80, so for example minus 100 or minus 120, there's a reversal potential in which potassium ion will then come inside of the cell. So that's the way the equilibrium potential works. And in the equilibrium potential, it favors, it counts for the electrical part. There's a chemical, so it takes into account the electrical gradient, chemical gradient, the temperature, and the charge of the ion itself. Yeah. And so the sodium potassium ion pump is basically the pumps that moves 3 sodium ion inside of the cell and 2 potassium ion outside of the cell. Yep. Wait, what? No. It's the no. Sodium potassium ion and sodium potassium ATPase is the one that pumps sodium outside of the cell and potassium inside of the cell. Also, although the sodium potassium ion is important in generating the resting membrane potential, most of the resting membrane potential is generated by this potassium channel. So although the sodium potassium pumps 3 sodium ion out and 2 potassium ion in, which generates the membrane potential, and the chemical and electrical gradient, the one that actually makes the membrane potential very negative is actually the potassium ion channel. Yep, I already know all of this. In a resting membrane, yep, permeable. Yep. So if you look at this, when there's only potassium ion channel and there's no net movement of the because although the chemical gradient favors the pumping out or the efflux of the potassium ion channel, the electrical gradient favors the pumping in of the influx of the potassium ion. When there's one sodium ion channel though, as you can see, the sodium ion channel is open, then both the chemical and electrical gradient actually favors the influx of the sodium, because there's a lot more sodium outside of the cell than inside of the cell, and also inside of the cell very negative at the resting membrane potential. And so both electrical and chemical gradient favors the influx of the sodium. And when sodium goes inside of the cell, then it depolarizes the membrane potential, which makes it more positive. And when it's more positive, eventually it will favor the efflux of the potassium, because now the electrical gradient also favors for the efflux of the potassium, right? Yep. So tired. Electrical synapse. So with regard to electrical synapse, cells are said to be electrically coupled when they basically have this what we call a connexon. So so one connexon composed of 6 connexons. So when you have the gap junctions basically, and this connexons is kind of like pore called the gap junction. It allows for the movement of the ions in and out of the cell, and it's very fast. The transmission of the signal is very fast because it's physical coupler, right? It's physically connecting to each other. And so yeah, and so electrical synapses, unlike most chemical synapse, is also bidirectional. So difference between chemical synapse and electrical synapse is that electrical synapse is bidirectional and very fast because it's electrically coupled, physically coupled, and synaptic integration. So when there are several postsynaptic potentials that integrate, it may actually fire action potential. And a component of the chemical synapse, there's a presynaptic neurons and a postsynaptic end, postsynaptic neurons, right? So it can be neuron, it can also be muscles. Sometimes it's muscles, so that one we call it neuromuscular junction, right? And so in here in the synaptic cleft, you can see that there's a vesicle that is being docked at the presynaptic end, and then those docked vesicles release release a neurotransmitter, and the neurotransmitter bind to the receptors that exist on the postsynaptic end. And as you can see in the presynaptic end, there's a lot of the docked vesicles, and also there's a lot of mitochondria. And remember, there's no microtubule at the postsynaptic terminal. In microtubule, only the microtubule is only present from the axon hillock until at the axon proper. There's no microtubule on the axon terminal. And yeah. And also there's a lot of the receptors on both presynaptic and postsynaptic membrane, because in the presynaptic membrane you need those calcium ion channels to basically pumps the calcium inside for them to be able to release the vesicle. And also sometimes there's the autoreceptors. So autoreceptors are basically those receptors that binds to the neurotransmitter and kind of like modulate or regulate the presynaptic neurons at presynaptic axon terminal, which will affect the probability of the release of the neurotransmitter. An example of this is the endocannabinoids, which is released by the postsynaptic neurons, which affects the presynaptic neurons. So this is what we call a reverse signaling. Yeah. So there's a type of synapses. So axoaxonic, axodendritic, axosomatic, axospinous, and dendritic. Right, and then and then the neuromuscular junction. So it just goes to the muscles, and then from there it leads to the contraction and the movement of the actin and myosin, right, which leads to muscle contraction or relaxation. So with regards to the acetylcholine receptors, there's two types: ionotropic and metabotropic. Ionotropic is the nicotinic, and the metabotropic is the GP-star, which is the type of the muscarinic one. And so over here, chemical synaptic transfer, there's neurotransmitter synthesis. Usually the synthesis is in the soma, right, and then loading of the neurotransmitter into the. Sometimes it can also be in the axon terminal, actually. So it depends on the type of the neurotransmitter itself. Something can be synthesized in the axon terminal. Something can be synthesized in soma and then packed into the vesicle, and then the vesicle is being transported into the axon terminal, being docked there, and then vesicle fused to the presynaptic terminal, and then from there binds to the postsynaptic receptors, and then biochemical or electrical. So it's always like this. So electrical, chemical, electrical, right? And types of the neurotransmitters, so there's the amino acid type, the peptide neurotransmitter, and also the amine. So for amines, for example, is dopamine, serotonin, norepinephrine, and epinephrine. So for dopamine, norepinephrine, and epinephrine, the precursor is actually tyrosine, the amino acid tyrosine, and tyrosine undergoes a lot of the biochemical pathway to make the dopamine, norepinephrine, epinephrine, and they're basically important in attention, in movement, in mood as well. The fight or flight response. And an amino acid, for example, glutamate, GABA, and glycine. So glutamate is the main excitatory neurotransmitter. GABA and glycine is the inhibitory type of neurotransmitters. Peptides, for example, dynorphins or enkephalins and stuff like that. So yeah. Yeah. I already know this. Yeah. And the mechanism of the neurotransmitter release. So basically, in order for you to be able to release the neurotransmitter, you need to have influx of the, calcium, right? So what happened is that at the axon terminal and near the synaptic cleft, there's this the although the presynaptic neurons and the postsynaptic neurons are not connected physically, sometimes they're tethered together by membrane bound protein. So like integral protein. Wait, I forgot the name. Integral protein. Integral integral protein. Integral protein. Yeah, integral protein. I forgot the name exactly, the exact name, but basically on these membrane-bound proteins. So, for example, cadherin or neuroligin and neurexin. Neurexin is the one at the presynaptic, and neuroligin is the one at the postsynaptic. And they're tethered together, and the reason why they're tethered together is to bring them closer, and also one of the V snares, one of the snares complex, one of the snares protein actually actively recruits potassium, no, not potassium, calcium ion channel near the docking of the vesicle, and therefore the potassium can come in. When potassium comes in, it leads to the binding to the synaptotagmin. There's four bindings of synaptotagmin. Synaptotagmin then leads to the conformational change in the synaptobrevin and the SNAP25, which is the V snares and the T snares, and then through conformational change, it leads to the release of the neurotransmitter towards the synaptic cleft. So there's two mechanisms, proposed mechanism for this release of the neurotransmitter. There's the kiss and run, and also the complete integration of the vesicles into the plasma membrane of the presynaptic end. And so yeah. It's gonna be sort by endocytosis or something like that. Yep. Thank you. So stressed. Oh my god. My exam is in like 1.5 hours. Just 1.5 hours more before my exam. Belum selesai. Nata I got though. Okay, and so basically, with regard to the calcium ion influx, so what happens is that, remember that during action potential, there's the depolarization, um, and at the peak of the action potential, the membrane potential is really depolarized, and so it's really positive. So although the initial depolarization activates the calcium ion channel to be open, there is no electrical gradient for the calcium to come in. Although extracellular calcium is usually higher, there's no electrical gradient for the calcium to come in because the membrane potential is already very positive at the peak of the action potential. However, during the falling phase, when the potassium ion channel starts to basically get activated and there's an efflux of the and the membrane potential gets hyperpolarized, starts to get polarized and hyperpolarized, and rapidly gets negative, that is when there is an electrical gradient for calcium to come in. And so then calcium coming in, and when the calcium comes in, it binds to the synaptotachmin and leads to the fusion of the membrane vesicle and release of the neurotransmitter. Yeah. And there's a synaptic physical and frontal transfer release. So basically, the miniature end play potential is when you have. Oh my god, my eye is so itchy. Oh no. Is this lagging? Any lagging? Is this lagging? Maybe it's lagging, I don't know. So basically the miniature end plate potential is basically the amount of vesicles that what I found is that one miniature end plate potential is generated from one physical release. Yeah, so it's miniature end plate potential is generated when there's very low amount of calcium that coming in. And exercise, yeah. Should be transient exercise rates up there. So EPSP is basically excitatory postsynaptic potential is basically when oh my god, I'm so sick. Bruh. My eye is so itchy. Okay. So EPSP is basically excitatory postsynaptic potential. It's a transient depolarization of the membrane potential after the binding of the neurotransmitter on the postsynaptic end, which leads to the increase in the probability of generating action potential. While IPSP is basically an inhibitory signal to transient hyperpolarization or polarization of the membrane potential that leads to the decrease in the probability of the release of release probably of the making of the AP. Usually the IPSP is because of the activation of this either the potassium ion or the chloride ion. So activation of the chloride ion is usually by the GABA, the GABA or lysine, and they're also affected by ethanol, barbiturin, and then benzodiazepines. And other receptors, I already know that. So you already know this. Quantal release. Yes, quantal analysis is basically to determine the amount of vesicles that is released during the neurotransmission. Synaptic transmission. Yeah. Alright, the synaptic integration and summation. So basically, there's the temporal summation and spatial summation. Temporal summation is basically when the summation happens when there is a release of when there's a, I guess, membrane depolarization that happens at the same synaptic end in a consecutive series in rapid succession. So EPSP is generated at the same synapse in rapid succession. The spatial summation is when the EPSP is generated at different sites of synapse at the same time. And then when it's generated at different dendrites, you can basically have the linear summation when it's generated at all the different sites but same dendrites. You cannot have linear summation. And when you have linear summation, you can eventually pass through the threshold for the action potential and generate action potential. And then there's something effect, which is basically the inhibition of the movement of the positive current throughout from the soma to the axon hillock because of the inhibitory, because of some IPSP. There's an IPSP. Alright, and you need to know that the EPSP and IPSP, the depolarization and hyperpolarization, they basically decrease in, I guess, strength along the dendritic cable. And so yeah, decreasing depolarization along the dendritic cable because it's not action potential, it's just the M plate potential, right? So but then sometimes the sodium channel dendrites can act as an amplifier. I already know that. Oh my god, my eyes are hurting so much. Should I wash my face? Wash my eyes? Jesus Christ. I think I already know all of this. I know everything. No, I don't. Kinda, yeah. I mean, in general, I know most of these. I don't understand. Okay, I know that. I know everything. Yeah. Should I buy like eye drops? I feel like I should buy an eye drop. Come with me to buy some eye drops. I hope there's an eye drop. Do they have eye drops? Maybe they don't.
내려갑니다. 1초. 인층입니다.
They don't have eye drops. I guess I should buy eye drops at a pharmacy. Like, I don't think they have eye drops. Yeah, what is this? It's not the fancies, they're not eye drops. Eye drops 없어요. Now, let's study again. Chapter 7, the structure of nervous system, importance of neuroanatomy, blah 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 blah. Cerebral. So I just need to know. There's the brainstem, the cerebellum, there's cerebrum. And the brainstem connects it to the spinal cord, and the spinal cord is kind of like the conduit between the CNS and also the rest of the body, or the PNS, I guess. Yeah. So there's the what do you call that? The frontal lobe, the midbrain, and the hindbrain. But we're not going to talk about the hindbrain. We're going to talk about the midbrain, frontal brain only. So basically, yeah. So basically, with regards to the cerebrum, the cerebral cortex is because the mammal cerebrum is very, very large and very large surface area. But then our skull is like the same size. They basically need to convolute. There's convolutions on the human cerebrum so that they can fit inside the skull. So that's why there's a lot of the wrinkles in here. Wrinkles in the cerebrum part. And then there's the dorsal, which is to the back, ventral, which is to the stomach, and then posterior and anterior. Anterior is towards your head, posterior is towards your tail or your butt, which is rostral and caudal. It's just the same. And then here you can see this is the cerebral cortex, and then there's thalamus, and then this is the cerebellum, and from the cerebellum extends the what do you call that? Brainstem. This is the brainstem. And the brainstem consists of the midbrain, the pons, and the medulla. And then there's a lot of these important structures like the hypothalamus, hippocampus, amygdala, thalamus, and stuff like that. So central nervous system is basically the brain itself and also spinal cord. So the brain and spinal cord makes the CNS, and the PNS is basically any type of nervous system that is outside of the CNS, right? So central nervous system, there's a cerebellum, cerebrum, and spinal brainstem, and also the spinal cord, right? PNS is outside of that. And so with regards to the organization, so the spinal cord is attached to the brainstem. Remember, the brainstems connect the brain with the spinal cord, and the spinal cord is kind of like a conduit of information between the brain and the rest of the body. It controls the skin, joint, muscles, and the dorsal root ganglion. Dorsal root ganglion soma is outside of the spinal cord, but then its axon actually innervates the spinal cord. And so for somatic PNS, for example, it innervates the skin, joint, muscles. For a visceral PNS, it controls the internal organ and blood vessels. Yeah. And then efferent, I already know this. Easy. Cranial nerves, 12 nerves from the brainstem. Remember that the brainstem, mostly innervate the head. So now I can barely see because my eyes are swollen. So tired. And then for the organization of the skull from the brain and like the tissues and stuff, there's the meninges. Meninges consists of the dura mater, the arachnoid membrane, and the pia mater. The dura mater is the most outer layer. And remember, between the arachnoid membrane and the pia mater is the subarachnoid space. The subarachnoid space is a part of the ventricle. So ventricle is kind of like a canal that is filled with cerebrospinal fluid, and a cerebrospinal fluid functions as a cushion for the brain when you have physical movement, so that the brain is not crushed by the physical forces. So it kind of like acts as a cushion, right? And so the subarachnoid space is a part of that ventricle system. And yet, in this, cerebrospinal fluid is made or synthesized in the choroid plexus. Yeah, choroid plexus. I just need to know that the CNS is derived from the neural tube, while the PNS is derived from the neural crest. And yeah, and the neural tube is kind of composed of the endoderm, mesoderm, and ectoderm. I feel like I've learned this before somewhere. I forgot. Ventricular system. Yeah, so basically, ventricular CNS forms from the walls of a fluid-filled neural tube, right? And then inside of the neural tube is the ventricular system. So remember how the ventricles that we talked about is filled with cerebrospinal fluid, and then one of them is subarachnoid space. So those ventricle system is ventricular ventricles. They're made from the neural tube. So basically, the neural tube gives rise to the CNS, which consists of the mesoderm, ectoderm, and endoderm. But then also within those inside of the tube gives rise to the ventricles, while the PNS is made out of the neural crest. So neural tube and neural crest, right? And so three primary brain vesicles: the forebrain, the midbrain, and the hindbrain. So prosencephalon, mesencephalon, rhombocephalon. So three part of the. So remember how it's like endoderm, ectoderm, and mesoderm, and so it's kind of like forebrain, midbrain, and hindbrain. Prosencephalon, mesencephalon, and yeah. I don't want to study about this part, differentiation of the forebrain. They're not part of the forebrain. Telencephalon, cerebral hemisphere, olfactory bulb, basal tussin. Diencephalon, thalamus and hypothalamus. Sensory and development. So the white matter is myelinated, man. I just need to know that the way it progresses is especially in the forebrain, is that from the PNS it goes to the thalamus, from the thalamus it goes to the cortical areas, which is the cerebral cortex, right? And so from the cortex to the thalamus, the axon goes through the internal tube, internal capsule, and then from thalamus to the cortex also goes through the internal capsule. Yeah. Well, the midbrain one. Remember how the midbrain is like from the brainstem into cortex to brainstem and spinal cord. Tectum is composed of the superior colliculus and inferior colliculus. Superior colliculus is the one. Remember, superior colliculus is the one that basically directs or points the eye towards the target object in response to new stimulus, and inferior colliculus is one of the pathway in the sound perception, auditory perception. So there's the tectum, and then tegmentum. Brain, brainstem, and the spinal cord. And it also has the tectum, which is composed of the superior and inferior colliculus. It's really colliculus, superior, blah 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 blah, and then the tegmentum. It composed of the black substance or substantia nigra, black substance, and red nucleus. What is this for? Voluntary movement. So there's tectum and tegmentum. Forebrain is specifically for the cerebral cortex where the information is processed, right? So to convey the visual information, sensory information from the pianist into the thalamus to the vertical cortex. Okay. And remember the parietal lobe and the temporal lobe. So temporal lobe is for the basically visual motion, right? For the parietal lobe is for directionality and navigation. Okay, then. Taste. There's the saltiness, sourness, bitterness. So the tip is sweet, bitter, salty, sour, and sweet. Papillae. Apical ends composed of the microvilli, which is like taste spores, so it can either directly undergo them and something again. And it passes directly through ion channels, bind and block ion channels, or it can act as a ligand for G protein, GPCR. So for example, saltiness, sodium ion coming in, and then sourness because of the proton then comes in for depolarization. And then bitterness is T1R and T2R. Well, the sweetness is T1R2 plus T1R2 and T1R3. Both are required. Umami, T1R1 and T1R2. T1R2, T1R3. Cranial nerves, gustatory nucleus, the primary gustatory cortex, localized lesions, acute loss of taste perception, acute gustation, important for the control of feeding and digestion, hypothalamus and basal thalamus. So it goes from the gustatory nucleus towards to the VPM. What's a VPM? VPM? What's a VPM? Left ventral posterior medial nucleus of thalamus. Oh, okay, thalamus then. The cranial nerves, so the gustatory and primary gustatory cortex. So I just need to know cranial nerves, and then towards the gustatory nucleus, towards the primary gustatory cortex. Olfactory nerves, smell key components, order inside. Sucrostin, cellular AMP, and then from cellular AMP, then activation of sodium and calcium channel. Is a member in depolarization. Ah, I see. This is essay. Oh, I see, I see. Olfactory neurons. Septocellular. The olfactory bulb. And from there, from olfactory receptor cells towards the olfactory bulb. And then from olfactory bulb, cyclic reticular channel. The opening of the cyclic nucleotide gave the channel into olfactory receptor neurons, ORN. So that's why the cyclic AMP. Other beings. Inhibition. Some sort of overture measure for neocortex. Oh, dorsal nucleus of thalamus. So from the olfactory receptor cell to the olfactory bulb, from the olfactory bulb to the olfactory cortex, in the forebrain. Branched through the kind of pathway, medial dorsal nucleus. Medial dorsal nucleus. And there's the medial nucleus and lateral nucleus. This is medial dorsal. What's a geniculate means? I will be doing this again. I'm so tired. I think I should go soon to the exam because I need to take the exam. I'm gonna take the exam soon, so I need to go. Wait, what's happening? Okay. Bye bye, everyone.